Hi, class, and welcome back to Calc 3. This is the last day of lecture, which is kind of emotional. It's strange that class is ending this way. I've never lectured online like this before. It's been a whole roller coaster ride, but I want to say, thank you for staying along with it. For people who watch the videos, who sent me emails thanking me for what I've been doing and letting me know, albums that they've been listening to and songs that they enjoyed listening to from the albums that I recommended. All of it was appreciated. It's been good to feel somewhat connected to my students during these times which we're living in. So today's album recommendation is the 2009 album These Four Walls by the band with the best band name of all time, We Were Promised Jetpacks. They are a Scottish post-rock, guitar-heavy, like math rocky type of band. Post-rock, the lead vocalist has kind of a shouty voice. He's really distinctive. I would say that their music is largely about the guitars and drums and the instrumentation, but the vocalist kind of fits into it really well. This is one of their early albums and was really the one that captured my heart, but I like a lot of other music by them too. It's an album that I've listened to before on car rides where there are thunderstorms out, or just when it's storming outside and I'm alone in my house. These sorts of, settings where you want to be alone but hear someone else who's alone but making a lot of noise. They recorded this album entirely in a house that the whole band was kind of cooped up in I think it was Glasgow in Scotland or outside of Glasgow. But this has that sort of Scottish, lonely, ennui sort of feel while being a real, aggressive rock forward, guitar forward album. I saw We Were Promised Jetpacks in concert a couple times now, and the first time I saw them, I just remember thinking that they knew how to end a show the right way. They all were hunched over, like L brackets, playing their guitars really quickly for, they're playing up on the downstroke and upstroke, for this 12-minute riff on one of their best songs. And at the end, they all just left their guitars still sustaining, miscellaneous notes and feedback on the ground, and all stumbled off the stage together, and the crowd was cheering for them to come back to an encore while the dissonance of the guitars just kept kind of amping up in the speakers. So maybe this is the type of music you need at this time. I re-listened to this album yesterday, and it just brought me a lot of joy. So okay, that's a long enough intro. So today we're talking about the shape of things to come. So let's take a stock of kind of this picture of many fundamental theorems of calculus that we've talked about, and the many types of calculus that we've done over the course of Calc 1, Calc 2, Calc 3, and how we can make sense of this picture and maybe move it up to 4 dimensions, 5 dimensions, 6 dimensions, and see where calculus goes as we go up. So let's start with the Calc 1 picture. So in the Calc 1 picture, we were obsessed with functions on R1. And we looked at C infinity functions, so that's infinitely differentiable functions, from R1 to R1. And if we had a function living inside of here, what we could do was produce its derivative, right? And so we had this take a derivative operation, which took a function and produced another infinitely differentiable function. And I'm going to focus on the infinitely differentiable ones because that's just where it's easiest to state these sorts of things. And in Calc 1, you learned about taking derivatives. And then in Calc 2, you learned about integrals and the fundamental theorem of calculus and how you can undo differentiation in certain cases, right? And so this was kind of the big setup that you had to make sense of lots of different problems. And so if you had integrals that were hard to do, as long as you could figure out the antiderivative, you could compute something meaningful about these sorts of integrals by undoing differentiation. So, this little diagram, I'm telling you, captures the fundamental theorem of calculus in the Calc 1, Calc 2 context. And all of this is essentially single variable calculus. In Calc 3, in this class, we started moving up a dimensions. So in R2, we discovered that in order to make sense of, we couldn't just take derivatives. Instead, what we could do is take one of our C infinity functions on R2. So these are scalar valued functions. On R2 that are infinitely differentiable. And they're scalar value because they're taking value in R1. So that's scalars, right? And if I have one of these functions, sorry, that highlighter button is just exactly where I always want to grab it. Right, we had a function, let's say, of x and y. We discovered that the replacement for derivatives was going to be the gradient. So we had the gradient that took f to the gradient of f. And what type of thing was the gradient of f? It was a vector field. So it associated to every point in R2 a vector in R2. And the interesting thing we discovered about vector fields is if I have some vector field, let's not use f, let's use g. In R2, I have an operation on them that we care about called curl, scalar curl. And we were writing that as this, or curl, right? I'm trying to denote these operations here as what you would apply to f to get the next thing. So you would take the scalar curl, nabla cross, blah, of g to produce the scalar curl. And the scalar curl was a scalar valued function on R2. So we're back to scalar valued functions on R2. And we notice something special, which is that if you have a gradient field, like gradient of f, then when you took the scalar curl, you got 0. Right, so we're in this kind of interesting, special, do something twice situation, you always get 0. And then we introduced 2 versions of the fundamental theorem of calculus. And so we have the fundamental theorem of calculus for line integrals, which said that if you are computing the flow of a vector field, which is a gradient field, along some curve C. Then by the fundamental theorem of calculus, you can turn that into something about just f. Oh, I shouldn't have put a vector over f. It's a gradient. Yeah. F at the end minus f of the start. Right? But we also had an additional version of the fundamental theorem of calculus, and this is Green's theorem. And so I'm just going to call this also the fundamental theorem of calculus here. Let's just say all the blue things are fundamental theorem of calculuses. So here's a little legend. This is going to keep denoting a fundamental theorem of calculus, going backwards. So, and why have I drawn it the way I did? Is because the way we apply Green's theorem was we said, hey, maybe if we've got a double integral of a curl, so the curl of some vector field G, dA over a region, we can, by Green's theorem, move it backwards into a question about the vector field that it came from. And that question looks like you take an integral around the closed boundary of R of the flow of G. Right, and we also had the flux form, which I'm just going to kind of ignore for now, but because it doesn't quite fit into the picture as well. So it is worth noting that basically by relabeling, you can turn Green's theorem in 2 dimensions into something about divergence, but divergence doesn't quite fit into the picture in 2 dimensions because the divergence of a gradient is just something. It's not necessarily 0. And this going to 0 property was pretty important. So that's R2. Right? We have these 2 different versions of the fundamental theorem of calculus. And then in R3, we ended up with 3 versions. So we kind of can start seeing that there's a pattern. We had one version when we were working about functions on R1. When we started thinking about functions on R2, we had 2 different operations that we could deal with that we could undo by doing fundamental theorems of calculus. And so now let's go to R3 and see what the picture looks like there. I'm going to scroll down this far, so I got some space to write. So what do things look like in R3? Let's align. There we go. So in R3, we can start with a function from R3 to R1. So this is f, and these are scalar valued functions. And we have one operation on them, which is the gradient that produces vector fields. And these are now vector fields on R3. Right, and so f turns into the gradient of f. Now, likewise with above, gradient fields become 0 when I apply the curl. So I'm going to put the curl into the next step of this picture. But curl in 3 dimensions produced another vector field. Right? So rather than going rather than returning back from vector fields to scalar functions like we did up in R2, in R3 things are still kind of complicated. We're still working with vector fields. But then we have this other operation that now fits into the picture, which is the divergence, right? Which can take, so I wanted to write each of these. So this G goes to the curl of G, and I guess I'm going to use H for my next vector field, would have to go to the divergence of H. And the interesting thing about divergence is we learned divergence of a curl. So if I start with this curl of G, that also goes to 0. So we are in a situation where we have kind of like two of these chains where something maps to something which maps to 0. This G turns into something which always goes to 0. And that's how we kind of stitch together these sequences, and that's how I'm determining which order to do them in. That's why I did curl in the middle, not divergence. So, and divergence produces a C infinity function from R3 to R1, which means that is a scalar valued function. And the picture is that we actually get three fundamental theorems of calculus. So we get one for each of these, going backwards. And I always think it's easiest to remember what they are by starting on the right and then going to the left. And so I'm going to do each one underneath. And I'm going to line them up with the notation I used for each map. So over here, if you have something, an integral of a scalar valued function, so this is going to be a triple integral of a divergence dv. So because it's a scalar valued function, and I'm working in 3 dimensions, I kind of think I need to have 3 dimensions of input, which is why I know I start with the triple integral here. Then the divergence theorem tells me that that's the same as taking the double integral, let's give a name over my region R, over the closed boundary of R, of the flux. Now, I'm going to just switch colors to make sure clear these are different. I also have a one associated to curl, right? And so what is that going to look like? It's going to have to do with this, these two terms. And so if I start with a double integral of the curl of G dot n hat ds, so this is my local circulation, or circulation on surface. Integral, whereas this is the flux across surface integral. Then, and let's give a name, let's just use R again. Then I could pass to the boundary of R and get just G dot dp. Along the boundary. And this is Stokes' theorem. And I also have an additional one over here, which the form of which will look like I take a integral of the gradient. So that's going to be an integral of the gradient of f along some curve c. And I get back the integral, just f evaluated at the end and beginning of the curve c. So this is still the fundamental theorem of calculus for line integrals. It's just now that C is happening in 3 dimensions. So my picture for this might be that C is some complicated windy path in 3 dimensions. My picture for the middle one is that I've got R is this 2-dimensional surface, and the boundary of R is that circle. And then for this third one is that I've got some solid region, and I'm going to shade it in to denote that it's solid. And so it looks something like that. That's R, and the boundary of R is the sphere. So here are our 3 different theorems, and I'm just going to point out a couple patterns here happening in each of these pictures. And I'm going to zoom out just a little to see them all. So, the key thing is, if you start at the right, you're starting with triple integrals, and then going to double integrals, and then going to single dimensional integrals, so like line integrals, and then going to evaluation. In 2 dimensions, we start with 2-dimensional integrals, we go to line integrals, and then we go to evaluation. And in 1 dimensions, we're on integrals, which are line integrals, and we go over to evaluation when we apply the fundamental theorem of calculus. So in general, there is a reduction of dimension, as you go left. As you go left to right. The other cool thing in this pattern is we notice that there's kind of this difference here where we start by looking at scalar valued functions. We went up to vector fields. We stayed at vector fields, and then we went back down. And in the examples above, we also kind of changed target dimensions. So we're always starting with functions defined on R2, but they're either scalar functions or vector fields or scalar functions. And there's something about these patterns of these other numbers that I'm going to draw out. I'm just going to go to the next slide to see what it looks like. So here's the pattern, and I've drawn it in a suggestive way. So for R1, we have, what we had was we took derivatives. So this was dx. In R2, we had gradient and then curl. And the gradient went from functions valued in R1, scalar valued functions, to vector fields valued in R2. And then scalar curl took vector fields and produced scalar valued functions. In R3, scalar valued functions, so valued in R1, went up to vector valued, to scalar valued. So just to be clear, this one's my gradient. Here's my my curl, my vector valued curl, and here's my divergence. And I'm just going to draw in, there is a picture corresponding to this in degree 4, and here are the dimensions of the targets. You start with scalar valued functions on R4, then you go to vector valued functions, which take a point in R4 and give a vector in R4. And this is definitely the gradient. It's always going to be the gradient, this first one. But then it turns out that there's a kind of interesting operation, I'm just going to call it D, that lands in R functions from R4 to R6. And then there's another operation, I'm just going to also call that D, even though these two things are different because they're moving between different points, but you'll see why in a second. that lands back in vector fields. And then finally, there's another operation I'm just going to call d again that lands back in scalar valued functions. And the reason I've drawn this suggestively like this is that these numbers arrange into Pascal's triangle. So if you want to get one of the boxes, you add up the two boxes above it. So 2 plus 1 is 3, 3 plus 3 is 6, 3 plus 1 is 4, etc. So this gives you a big Pascal's triangle. Definitely need an N in there. Triangle. Yeah. And why don't I actually write out the formulas for what happens in R4? Although before doing that, let's just point out we can already now guess how many fundamental theorems of calculus we get. Because for each of these, we got a fundamental theorem of calculus for every one of these arrows, right? So we got 3 in dimension 3, 4 now in dimension 4, and so on and so forth, right? And so we get this whole big Pascal's triangle that tells me what types of formulas I'm going to need to write down. So I need to tell you what these d's are, and then on each formula for the d will give you a version of the fundamental theorem of calculus in that dimension. And you can continue this, and like in R5, these dimensions become 1, 5, 10, 10, 5, 1. In dimension 6, they become 1, 6, 15, 20, 15, 6, 1, and so on and so forth. So let's look at, in particular, the ones for R4 to give you a hint about the type of complications that show up. So in R4, we're going to get a bunch of new operations that relate functions on R4, scalar valued functions, to vector fields, to whatever these things in the middle are, which look complicated, back to vector fields, and then down to scalar valued functions. I've color-coded my differentials D, so the red D, the blue D, and the green D are all going to be different, and I'll give you the formulas for each in a second. And I'm not really going to explain how these formulas come up, but I think you'll be able to see that they have patterns sort of like what the formula for divergence and for curl are, but it's kind of hard to know systematically how to produce them, but in a formal real analysis class where you would learn how to do calculus in arbitrary dimensions, you would learn exactly how to produce these formulas. So, but let's write down the one we can always write down, which is grad. So if I have a function here of, let's write it as xy, I think wxyz. So we've got 4 variables. Then I definitely know what the gradient of f looks like. It's a 4-dimensional vector field where the first one is fw, so that's df dw, and then I've got fx, fy, fz. To make sense of the red map, I should tell you what it sends a vector field. So I'm going to write that vector field as m, n, p, q. So it has 4 different functions. So each of these is like a function of w, x, y, and z. N is as well, p is as well, q is as well, just like in 3 dimensions, just now I'm up in 4 dimensions. And I'm going to send this to d of something. So let's just call this vector field g. So d of g, and let me give you a formula for d of g. And I'm just going to make it magically appear here. So this might look a little strange, but notice that it has 6 coordinates. So I've got the first, the second, the third, the fourth, the fifth, and the sixth, because this has to produce a 6-dimensional vector, but it's only taking inputs in 4 dimensions. So it's some strange type of function. It's not a vector field. These are sometimes called two forms. Yeah, but it's this function that takes something in R4 and produces something in R6. Essentially, though, this is keyed up so that we have the following truth. If I take the red d differential of a gradient, I always get 0. And so I still want that to be true, and this formula will force that to be true. So you can see that it's kind of, so like, for instance, why is this first one true? Well, if it's a differential, Q is actually Fz, and P is Fy. And so when I take these Qy, I'm taking Fzy, and when I'm taking Pz, I'm taking Fyz. And if F is infinitely differentiable, the mixed partials are equal. And so this is just checking kind of that each of the mixed partials is equal. But there's, it turns out, just by combinatorics, 6 different ways to check that, because that's what it is when you compute 6 choose 4. 4 choose 2. So that's just why I have this many dimensions here, is because that's how many things I need to check to see whether F was a gradient vector field, or G was a gradient vector field. And now remember that what I want to be true in order to have a fundamental theorem of calculus is that if I do the red differential and then I do the blue differential, I should also get 0. So any 2 steps in this sequence should give me 0. So step, step should give me 0, and step, step should give me 0. So if I send the red d of g to d of g, that will also equal 0. And so let me tell you additionally what that sends. And I have some space here, so I'm going to write it. So D needs to, in general, take one of these kind of like 2 forms, these 6-dimensional vectors that are made up of components, each of which is a function on 4 dimensions. So I'm just going to write that as A, B, C, D, E, F. And I'm going to tell you where it goes. So it goes to D of, let's just call this H. And what is D of H? I will write it down here. And now again, this formula is going to look bad because this should be something like curl or one of these complicated looking formulas. And it needs to have this special property that it gives you 0 when you apply the red D and then the blue D. Poof! Here's the formula. Now, I want to be clear. Don't memorize these formulas. Just don't do that. That's a bad idea. In a real analysis class, you learn how to produce them, and there's some combinatorics that go into them. So they're not a formula you memorize. They're a formula you learn the machines for producing, and then if you ever needed to produce them, you could write them down. But you can see that there's some patterns in these. So over here, everything has positive signs, and then here I have like 2 negatives. Here I've got 1 negative. So like I'm kind of doing the 2 different ways of mixing the negatives, and then here I have all negative signs. And it so happens that this formula gives you that D of G of any G will always equal 0. And finally, there's this green one. It actually turns out this is divergence. So some people write it still like this, or just divergence, but this really does send a vector field. Let's just use I for my vector field to the divergence of the vector field. And so that looks like if I is M, N, P, Q, which I, again, am reusing, but I have so many letters, this will look like M, W plus N, X plus P, Y plus Q, Z. And so in some sense, these outer ones are the gradient and the divergence. That's kind of always the same, and they're the easy things to do. It's kind of easy to imagine that you can take a function and take all its partial derivatives and use that to produce a vector field. It's also easy to take a vector field and then just take the like with like partial derivatives of each of the components of the vector field and add them up. What's kind of unexpected is how to produce these intermediary formulas that stitch together those two end parts. So in the same way that in R3, the formula for curl is just harder because it involves determinants. It's some sort of complicated combinatorial process that produces a function that fits nicely into this picture. So then you end up with, this fourfold sequence between these 5 different types of functions that gives you, it turns out, 4 different fundamental theorems of calculus. And it's also true that taking the divergence of D of any one of these two forms, H, in the center thing also is always equal to 0. So it's also true that each of these twofold steps goes to 0. So going here to here, that's this sequence goes to 0. Red, then blue, this sequence goes to 0. And then doing blue, then green gives you 0. And the reason that I'm emphasizing that is turns out to be like very essential to understanding why the fundamental theorem of calculus works, or proving it in the back end. But also there's this key distinction that it's different to say I'm starting with some, I think it's easiest to understand here, it's different to say that this goes to 0, than to say that if I have a generic vector field, it goes to 0, right? Like, so a generic vector field goes to something, this complicated formula here, and then when you apply the second differential, it goes to 0. So that's this sequence. But only gradient fields map to 0 under the red differential, and that's telling you something special about gradient fields on R4. A way to detect them, essentially the Clairaut test. So the final point I just want to leave with today is for each of these maps, you actually produce a fundamental theorem of calculus. So, and the leftmost one is still the fundamental theorem of calculus for line integrals. But these intermediate ones are kind of strange, and you have to make sense of what types of integrals to write down. And again, this would be something you'd learn about in a future class. But this is a sketch of what the sorts of tools that we've been building let you do in higher dimensions. They let you go and apply some combinatorial formulas to produce new versions of the fundamental theorem of calculus that let you produce, higher and higher computational results. In general, when you get in a future class, all of these higher versions of the fundamental theorem of calculus are just referred to as Stokes' theorem. And if you simplify your formula for what integrals look like, and so you stop writing like infinity integrals, 4 integrals versus 3 integrals versus 2 integrals or whatever, you'll end up with some sort of formula that looks like this. If you start with d of something, some f, whatever type of form or thing this is. So let's maybe put, you know what, let's use a lowercase f to make things as weird as complicated. So f might be a vector field or a scalar function, or one of these weird R4 to R6 guys that we've introduced. F is one of these many forms that I've applied a differential in this sequence to. And if I try to compute df around over some region R, and so R is happening in some number of dimensions, so like, yeah, well, I'll compare to our previous versions below in a second, then you end up with a Stokes theorem that tells you that this is totally the same as integrating whatever f was to start with in the appropriate sense around the boundary of R. So there is this interplay between passing from integrating something where you've applied a differential to move right in the sequence versus the thing you started with but applied on the boundary of the surface that you are working with. And so let's just compare this formula to each of the formulas we've seen so far. And so this is our proto-theorem. But it requires understanding what the two sides are. And I'm telling you, this is always, if this is an n-dimensional integral, this one will be n minus 1 dimensional. So, for instance, in R3, that looks like, hey, I know one of these sequences is I can apply divergence to some vector field, and the right-hand side, so this df looks like this. Here's what my df is. And I can integrate that over a three-dimensional volume. So this is a solid three-dimensional region. And I know that that's totally the same by Stokes' theorem to doing an integral over the boundary of R. And since it's the boundary of a region, it's always closed. So you always end up with these kind of closed integrals. So if you want, you can include the closed formula there to remind you that you're going down a dimension. And what does this look like? This now looks like f dot n hat ds. And so this is kind of the f that we started with. We have to understand what it means to integrate f. And so in the particular setting that we care about, when you just are given a two-dimensional closed surface, the way of understanding Stokes' theorem tells you that what you should be computing is flux through that surface of your vector field. So you get to move, this guy computing a flux integral into computing a divergence or a sum of local divergence integral. So flux integral sum of local divergence. And likewise, there's, this pattern persists, right? So if you want to look instead at Stokes' theorem looks like I'm trying to compute some sort of thing of curl of, I'm going to keep using f, why not? It's a vector field. And curl was always dot n hat ds. And so, again, I'm computing flux of the curl of f through a surface. So, and this is now some other surface. Let's use R prime for that, just to make it clear it's different. And Stokes' theorem tells me that, hey, if this is your df, then your f had to be just f dot dp around the boundary of R prime. And hopefully this helps make sense of what's going on. So always on the higher dimensional side, you are doing some operation to your thing, and on the lower dimensional side, you are doing the operation to this region that you're dealing with. So this is this interplay between, the slogan I want to end class with is really that Stokes' theorem interchanges partial derivatives on functions with partial derivatives on regions. Okay, but that's maybe a weird way to say this, because we wrote this formula twice, this expression, right? And so on one hand, we said that this is boundaries. It's a boundary operator. But on functions, it was really partial derivatives. And the common feature of all of div, of grad, of curl, of these higher dimensional D analogs that I wrote down is all of the formulas are defined in terms of some combination of partial derivatives. And Stokes' theorem, the fundamental theorem of calculus, is telling you how to change partial derivatives into some sort of information about taking a boundary of the region you started with. So that's why the fundamental theorem of calculus goes from integrals to the endpoints of the integrals. That's why Stokes' theorem goes from a two-dimensional region to a boundary of that two-dimensional region. That's why the two-dimensional Green's theorem goes from an integral over a region of a bunch of partial derivatives of it, either a divergence or a curl form for those partial derivatives, to a line integral. And line integrals are down a dimension. They're integrals over the boundary of that region. So hopefully, the whole point of today was to sort of justify why we used partial derivative as a boundary operator on our regions. And this is why. Is because we're going from something that involves taking partial derivatives of a function, maybe that function's a vector field or scalar functions or whatever, some other form, to ultimately boundaries of regions. And that boundary of a region thing is what reduces dimension. I think with that, we're going to stop. I recommend looking back over the last couple lectures where I've done a lot of examples, especially on Monday, computing with these different forms of Stokes' theorem and identifying what are the patterns for how I used it. And hopefully this will help kind of put everything in a bigger context so that you can find it easy to use these formulas. I'm going to post a review sheet probably tomorrow, and then on Friday I'll post my solutions to the review sheet as a video, and I'll talk more about studying for the final exam. Bye everyone. Stay safe.